Hi, welcome back to my math tutorial video thingy. We're gonna continue with non-right angles now. The previous two videos, if you check them out, they were on right angle triangles. Some very interesting math, just we understood the keywords and what ratios to take where. The next step, algebraically, turned out to be quite easy. A few number crunching activities, but then basically we got the answer. So please focus on understanding what the words are about, and then hopefully we can start to solve many different problems. Non-right angle triangles. We're going to start with the sine rule. We also have cosine rule and the area rule to worry about. But let's start with the sine rule. It's a very useful rule to deal with non-right angle triangles. So I made a little preparation for the formulas. The sine rule, this is one and the same rule. I wrote it in two different ways. You see, one is just, let's say the second one is just the flipped version of the first one. It just, if I write the length of the sides in the denominator or in the numerator, and consequently the signs of the angles in the numerator or the denominator, if I just do it consequently, then it doesn't really matter what I put where. I am just flipping this equation into that equation. The algebra will come out easier if the side of the length of the side is unknown, if I use the second variety. If I use the first one, it's more so handy when the angle is unknown. Okay, so I have a little math problem for you now. Let's say we have a triangle where A is equal to 29 degrees. So this is, you know that one angle is 29 degrees. You know that the side, lowercase a, which is now opposite to this angle, you remember the convention that we're using? The uppercase angle is opposite to where the lowercase side is. So that side is 5 units of length long. We have another side, let's call it C. We could have called it B as well. I'm just going to calling it C to keep our minds occupied. That's going to be 9 units long. So the question is, what is the size of the angle C? The size of the angle that's opposite to the other given side. So this here would be a typical sine rule problem. I'm going to start off by making a little drawing. Not accurate, but hopefully it will help me to understand the problem. Let's put my angle A here, and I have 29 degrees here. And so the opposite side would be 5, because that's my lowercase a. Let's say I put my C here. I don't know what C is, but I know that the opposite side is 9. I make the picture credible that the side length 9 is longer than the one that's 5, but I'm not going to sit down with the ruler and waste time, because on a test you only have a period's length, and I want to make sure that you understand the problem rather than having millimeter accuracy in your triangle. Okay, so how do I do this? Well, let's use the sine rule here. I have information about A and I want to find about C. So if I go back to my formula, and also it's the angle that's unknown, so I'm going to use the top one. I'm going to put my finger over the middle guy because I don't need it. So basically sine A of A is equal to sine C of C. Always you're going to put the finger over the one ratio that you don't need. Otherwise this would look weird if you have two equal signs on the same row. So let's put my finger on this one. So sine of A divided by the side length A is, so let's just copy paste this. Sine 29 degrees divided by 5. It's equal to sine of C. Well, I don't know what that was. I'm looking for it, so I'm just going to write C. But I'm dividing it by the length 9, which is my C here. Okay. So that's it. Once I wrote this down, I got a mark on the test already because I know the rule I'm using and I know which number goes where. However, I'm going to need my calculator to find sine of 29 divided by 5, for example. I am getting this is 0.09696. Please check with your own calculator. It's very important. And this now was equal to the ratio sine of C divided by 9. So I'm going to put it equal to sine of C divided by 9. So in order to get 9 of C, obviously I need to multiply by 9. So I get 9 multiplied by 0.09696. And this is equal to 0.87266. So this 9 times that is equal to sine of c. I was basically not doing anything else than solving for this guy when I multiplied my 9 up on the other side of the equality sign. So this is now equal to sine of c. So I know that sine of an angle is equal to 0.8 something. I don't know what the angle is. However, with calculators we can do magic tricks. We do the sine minus 1 button, the inverse sine of that number that we were trying to understand how large it was, the angle I mean. If I do this in my calculator, I will get something to the sort of 60.769 degrees, almost 61 degrees. Let's round it to 61 degrees. So in other words, I found my answer here, 61 degrees. So this would be a typical problem with a typical solution for the sine rule, but there is a messy, tricky little thing that we didn't mention. And that's the fact that if you look down this drawing of a triangle, I made this drawing up. How am I sure that this is the only possible solution? Actually, it turns out sine rule sometimes carries with it another solution with the same input data. And I'm going to show you what that solution is about. If I am taking this triangle, I'm making a straight line through from the top vertex straight down. Now this, let's say I have like a screw that's holding this wooden rod that's slanted on one side, and I'm holding it where the angle C is. And if I'm releasing it, this wooden rod is going to start to wobble around. But the length phi will still be the same, right? It's just going to shift around. Let's say when it's shifting around to the other extreme, it's going to go somewhere there. And it's still going to be 5. You see? It's like this side has moved. So this triangle, if you're only looking at this triangle, this could have been my starting picture. How did I know that it looked the way I drew it first? I had no idea. So this is another possible solution to the problem. It means that if I had 61 degrees here, there is another C here that will not be 61 degrees. And the question is, what is that angle? Well, we actually don't need to do too much to find the size of that angle, because I know that because I have a length 5 and a length 5, this is an isosceles triangle, the two side lengths are exactly the same. It means that the other inside angle will be also 61 degrees. So the length of these two, the size of these two angles is the same. And because this is a half circle, it's 180 degrees all around. A full circle has 360 degrees, right? So 180 degrees is this angle. It means that, let's call it C1. This angle is C1. So C1 will be equal to 180 minus C. Oh, sorry, that should be C, not 6 or anything. 180 minus C. So this is equal to 180 minus 61 degrees. And that's how I find the other angle. It's more or less equal to 119 degrees. So there are two answers possible. Two answers, exclamation mark. C is equal to 61 degrees or 119 degrees. And this is referred to the ambiguous case. It's ambiguous because the input information is not enough to specify one concrete triangle. There are two possible triangles that fit the input data, so we need to have two answers. Okay, just to finish this guy off, I will give you another example where the sine rule still applies, but it's only one possible solution. So it's the following case. Let's say that instead of a 29 degrees and lowercase a5 and c equal to 9, let's say I changed the side length of my a. Let's put 15 instead of 5. Let's think that now we have 29 degrees and then 15 and the same c is still 9. That means that this side will be much longer, right? Or this side, but let's walk with that side. So I have this a is 9, sorry, the c. Here my angle is 29 degrees. I know that my a will be 15, so to make the picture credible, it has to be much longer than the 9. So let's say it goes out there somewhere. I have something like this, 15. You can use the sine rule to calculate the size of this angle C. Please check carefully that you will get an angle C more or less equal to 17 degrees. I will not repeat, it's exactly the same calculation as we just did before. The basic message, however, is that here there is only one answer, because if I have my little pivot up here, where is the top of the triangle, and I'm using this as my wooden rod, and I'm letting it swing over to the other side, because 15 is longer than 9, this 15 will swing over, and I will not be able to create another, this 15 will never come up to the base again, because it is longer. It will come up somewhere here. It's not short enough to come down to the base to make another triangle, even though the angles will be quite extreme. So if this side length is longer than the other one that is given, then I only have one answer. One answer, and it's not ambiguous. So sometimes you will have triangles with only one answer. Sometimes you will have with two answers, and we expect to see both answers. Okay, thank you. Bye.